How's it going? My name's Alex. Today I'm just going to be going over 14.4, number 2. And for this one, all we're asked to do is find the equation of the tangent plane for a given surface at a given point. So not too bad. We can just kind of ignore the question itself for right now. I just want to rewind back to Calc 1, where once we learned how to differentiate itself, you might have been given a function like this and asked, what's the tangent line, not plane, but tangent line at a given point, like at the top of the hill. It'll be a flat line, but as you go along, it might be pointing up or down. And if you can remember how to do that, it's not too much of a leap to remember how to do the Calc 3 problem. So I'm just going to do a quick refresher. Now, the few things you're going to remember is the point slope form, or technically you could use y equals mx plus b, but point slope form. And you're going to remember that m, like your slope, is just going to be the derivative evaluated at the given point. So in this case, let's differentiate with respect to x, and we'll get 2x. And then at the point 2, 4, that's just 4, I think. Yeah. So then all we do is just plug in our points, and it's not too bad, Sorry. Y minus 4 is equal to 4 times x minus 2. And obviously you can simplify, but that is the technically a correct answer to the equation of the tangent line. And if you remember that, the Calc 3 equivalent is not too bad. It's just a small leap, because the only difference, obviously, is that there's just one more variable. So in our point slope equation for 2D, this is what it looks like. Now for 3D, it looks a little bit more chaotic, but it's not too bad to reason it out, hopefully. And this is really the only part that you maybe have to kind of memorize, or I should say, get familiar with. And if you'll notice, it's just the partials at each x and y. So while the tangent line is just with respect to x, obviously the plane has changing in both the x and y directions, so that's why we take the partial, is to account for that. So if you can remember all that, well, you're pretty much set for this problem. Hopefully not too bad. So the first thing that we can go ahead and do is let's take the partials of this function. So partial with respect to x, not too bad, just 1 over y squared. That might not jump out at you, but if you worked it out on paper, it should be pretty easy, I think, hopefully. And then with respect to y, that should be negative 2x over y cubed, if I remember correctly. Yeah, that sounds right. Alright. So now, we just have to evaluate it at the given point. So if we evaluate it, we'll get 1/4 for the slope in the x direction, and we'll get 8 over 8, so just 1 in the y direction. So you're pretty much done now. All we have to do is kind of plug it in to our 3D point slope form. So that would be z plus 1 is equal to 1/4 times x plus 4 plus 1 times y minus 2. And that should simplify pretty nicely. Let's see. Let us be z is equal to... That's pretty bad. Okay. Z is equal to x over 4 that 1 will cancel with. Okay. Plus y minus 2. Alright, so this is, that's the, oh, sorry. This is the equation for a tangent plane, so any point that's valid that exists in this equation, so any combination of x and y that gives a z, lies on that tangent plane, which I went ahead and graphed this out. And if you see, the red line right here is our tangent plane. Oh, sorry. And that blue sphere right here is our point. And as you can see, all of these points do exist, or do exist in that equation right here. So, yeah, that's pretty much it. Thanks for watching.